We'll start with a comment, a side comment that was related to some questions I was asked. So I described in my lecture that we can take, we described a particular case where we took the half of the Euclidean black hole and then we patch it to the Lorentzian black hole. And I described this classically, but this prescription also specifies the quantum state of all fields in the interior. So all fields in the interior of this geometry are specified by this prescription. And in order to understand how this works, you can just think about the usual description in Euclidean space, that evolving in Euclidean time from time equal to minus infinity to 0, that prepares the ground state wave function for all fields, for any theory, interacting or free or whatever. And the idea is that in a path integral description, you can view this as saying that you want to find the wave functional as a function of the fields. And so you specify some fields phi of x at t equal to 0, and then by doing the path integral with these boundary conditions, you find this wave functional. So that's some way of conceptually thinking about this. Of course, in ordinary quantum mechanics, you can very easily do this. In field theory, doing this is a little more tricky, but and not particularly useful in most cases. But it's a good way to conceptually think about how to determine the state, and the state is definitely determined by this prescription. The same works in de Sitter space. So in de Sitter space, you can think of half of the Euclidean de Sitter space, which is an S4, and this fixes a particular state in the de Sitter space, which is the usual state people think about in the de Sitter space. So that's why drawing these pictures is useful also. It also includes a specification for the quantum states of fields inside. Okay, that was just a side comment. So now we'll continue the discussion of wormholes. And what we're going to do now is a kind of wormhole phenomenology. Okay, so we'll try to understand what kind of wormholes there are. So we are going to start with the assumption that we have, let's say we start, the one we discussed so far was the one corresponding to the thermofield double. So we think that this geometry is dual to two separate field theories in a particular thermofield double state, which we've written down explicitly before. So write down. Okay, so that's we are going to start with this assumption, and then modify both the left and right hand side, and see what we get. Okay, and so with the assumption that this is true, then we are going to try to see what other things should also be true. So much of what basically all that I'm going to describe that right now was in papers by Schenker, Stanford, Roberts, and probably some other authors. There was also some aspects were also in a paper with Susskind, these authors with Susskind. So what we are going to do is we're going to just do a small perturbation of this state. So we're going to act with an operator, let's say on the left, on this thermofield double state. And this is an operator which is simply an operator that will could act here on the left, and it will create. So if you act with this operator, it creates an excitation that moves inward and falls into the black hole. Okay? And we're going to think that this creates a relatively low energy excitation with energy of order the temperature. Okay, so it's not a big perturbation on the black hole. Now it will be useful, so this is a picture of acting with the operator here and creating the excitation, but it will be useful to think of this as a state. So this, after we act the operator, we now have a state, and we can take this state and evolve it backwards and forwards. And from that point of view, what we have is this excitation that, well, then gets reflected here from the boundary, from the initial singularity. So if we view this as a state, the full time development of the state here in the interior, in the original theory, so without any perturbation, is a situation where we have an excitation coming out of the singularity and then going back into the interior. Okay. So if we assume this is true, then this is the correspondence in this particular case. Okay. Now we can insert this at any time, and so this time can be anything. And so here we drew the picture when the time is close to 0. But now we can, by the symmetries of the problem, take this time to be very, very early. And if we take that time to be very early, recall that the symmetry here acts as a boost here, right? And so if we do that, then we get a picture which contains the excitation roughly here. And for an observer who's sitting here at r equal to 0, here traveling vertically, this excitation now is highly boosted, because recall that we are doing a boost, so the symmetry is a boost. So translating back in time here acts as a boost around this point. And if we keep this dotted line the same, then the relative boost between these two is getting larger and larger. Okay. So we can, if we take this time to be very early, so if this time t1 is much less than minus beta, so very, very early, then we'll have a large boost factor.
TFT is also evaluated at t.
Yeah, so yeah, let's think of this as the state in the Heisenberg representation, right? So that's the state of the system. And so we think of states where W has different values of time as different states.
But TFT still the one.
Yeah, this one is always the same. And here what we were doing was applying this boost symmetry, which is a symmetry of this, but not of this. So it translates the time to the past, and it does this on the left-hand side, and the right-hand side is simply the same state, but evaluated at earlier time. So so here in this picture we have ignored the back reaction because this is a highly boosted particle. So now let's include it. And if we include it, then this will create a gravitational field, which is the gravitational field of a shock wave. And when you have a shock wave traveling this way, so if you have a light ray coming here, it gets displaced as you. So it gets displaced in the forward time direction. And in the end, you get a Penrose diagram, which has, well, here there is no modification. Before you, on this side there is no modification, but here you had this feature, and so you now the Penrose diagram looks more like this. So what this shift does is it moves this line a little further in, and now it falls into a singularity instead of coming out. So the continuation of this line onto the other side, it's hitting the singularity rather than coming out. So we now separated the horizons of the two black holes along this null direction. And so this is separated by some affine.
Black holes is the black hole before and after?
What?
It's two black holes. The future and the past, or the before and after of solving this. You say two black holes, we separate them, right?
Sorry, yeah, this is the black hole as seen from the. So here there are two black holes. There is the black hole seen from the right, and the black hole seen from the left, right? Two exteriors. One should not think of this as the interior. Okay, this is not the interior of the black hole. The interior of the black hole is this. This is a second exterior. Okay, that's an important distinction to make, and it's important to remember. Okay, so now let's continue this and think about the case where we have two shocks. So we have now W of T2, W of T1. So we have the state. So if we only had T2, so we we would create again the same excitation, but at time t2. And we're going to consider, the interesting case to consider is the case where t2 is actually less than t1. Okay? So this is a situation where we have some out-of-time order operators. We can consider whatever operator we want in the field theory. We just happen to want to consider this particular operator. Sorry, yeah. Yeah, so that's the state again. So here, this is the state in the field theory, here in the right-hand side. And what we want to find is what's the left-hand side picture. Yeah, maybe I should write, well, anyway. This will be in the right-hand side, and now we're going to write the left-hand side of this picture. And, okay, so we'll do this in some steps. So first, we have, let's first ignore completely the back reaction. So we have a particle that we create at, let's say, T1, and another particle which we create at T2, right? But again, we are going to think of this in terms of state, so there is something coming out of here, reflecting from the boundary, and similar picture here. Now, in order to really get a better picture, let's consider, so we're going to try to understand more precisely what this state is. So let's first imagine we have this initial state. So the state we think we understood very clearly in our previous picture. So let's try to understand the state before we acted with T2. So so before we acted with T2, so at this very early time, we had this this T1, this particle 1 that was created here, that was present in the state. Remember, here it was present in the state. And now we are creating, with the operator T2, we are creating the second particle that is going in. Okay? And now we just continue evolving this. And what we'll get here is we'll have some collision between these two. And the metric after this collision, well, it's might be complicated. But one of the features is that now, again, because we had this second particle coming in, this particle will be displaced inwards and might or might not reach the boundary. Okay? So depending on the relative energies of these two, it might be that this particle, which before was reaching the boundary, now might not reach the boundary anymore. Okay? So it might be that we might end up with a situation which looks roughly like this, where we have some here the collision geometry, and here we have the outside of this black hole, and and this particle which before was getting close to the boundary, now it's not getting close to the boundary anymore. Okay, so that's a new feature we can have. And in a very, in the case that this effect gets larger and larger, the effect of this collision, when the difference between these two times becomes larger and larger. And so in a regime where this difference of times is very large, turns out that the Penrose diagram roughly has a form of this, has roughly this form. So these are the trajectories of the two particles we have been discussing. This is the collision creates a singularity very close to the collision point. And the important point here is that now if we draw the horizons, so these are almost null lines, so they almost coincide with the horizons, this one here. So this is the exterior of one black hole, and this is the exterior of the other black hole. Okay? Yes, go ahead.
The sources of the boundary, is it okay to think of them as generating the particles by a half-retarded placent advanced propagation? Because you had the particle going in, the particle going out.
Yeah, I mean, so what we are thinking is that we are acting with this operator on the state, right? And this creates a new state. right? It's like acting with a B dagger on a state. So if in quantum field theory you act with B dagger at some time, right? Or the field operator at some time on a state, let's say the vacuum, right? So there are, you can view this is a new state, right? If you smear this a little bit, it will be a normalizable state. It's a new state, and it's a state which it basically near the time t is somewhat localized, and then it goes forwards, but then you can also evolve it backwards in time, right? This is the state we're discussing. And which propagator you use and so on depends a bit on what calculation you're going to do. But indeed, if you now consider, for example, the expectation value of some field, right, in the presence of this state, of course, the expectation value will be non-zero in the past also. So it's not the retarded propagator. Yeah.
To understand the shockwave picture that you do there, isn't it true that then the left moving mode that gets pushed along the right null ray?
Yes.
Because of the shockwave? Is that the picture there?
Here? Yeah, so here, yeah, that's essentially what the picture is here. So here I'm drawing, so I'm choosing coordinates here so that null rays just follow straight lines. These are not the coordinates that are used, so you can use some other coordinates where null rays just get a shift, right? So I've just shifted the coordinates in such a way that to draw the Penrose diagram in a more clear. So the standard way of drawing Penrose diagrams involves null rays that travel along 45 degrees, that they are not shifted, right? And that's what I've done here. So I've just undone the shift in drawing the Penrose diagram, right? And that's so first we drew this. We said, well, there could be when there is a shock wave in sort of some ambient coordinates, there is a shift, right? But now we redraw the Penrose diagram and doing that, and we get this this new Penrose diagram. Okay, so that's the picture. And now if we want to, so the first thing to note is that now the distance between the two horizons has gotten larger, right? It became non-zero. So here the two horizons were at essentially touching each other. So that's a special feature of the thermofield double. But what we see is that when we perturb the thermofield double in this way, we are led to a geometry where the two horizons are now far from each other, or further away from each other. That's point number one. Okay, second point is that that has the following consequence. So imagine that we are trying to compute the correlation function between two operators inserted on the two boundaries, right? So we have an operator O left here and an operator O right. And let's say that this operator has a dual which is a massive particle, then its correlation functions are going to be given by a geodesic, let's say, that goes this way. And well, this distance, the non-trivial part of this, it will be of order beta, right? But here it will be a bit longer distance, and so the fact that it's longer implies that this correlation function between these two operators will be smaller than it was in the previous case, than it was in the original case. And this was computed in greater detail in these papers. And it's found that even already in this case it becomes smaller, and as you take this distance to be, as you take this boost factor larger and larger, it becomes smaller and smaller. Okay. Yes. What? Yeah, let's say one question at a time. Yeah, the question? How do you get this diagram? Yeah, it basically comes from, well, you see, we already got this feature just from one of the shocks, that it got displaced in this way. And now we have the second particle, which at the moment of collision was traveling in the opposite direction, right? So now we'll have this fast-moving particle here. So let me take the boost in the naive description here. So we'll have one particle going this way, and the other particle going this way. So it's clear that when we add the effects of two particles, it's intuitively clear that we'll get from one we'll get the displacement this way, and from the other one we'll get the displacement in the other way. So that's essentially why these two got displaced in the way they were. And
But this is not a small perturbation on the initial geometry.
no, yeah. So it is, yeah. It adds very little energy to the initial geometry. So it's a small perturbation in that sense, but as a perturbation of the actual geometry is large, right? Because of the large boosts that are present in, or large redshifts that are present for black holes. I mean, what this is saying is that so when we acted with this, we deformed the state a little bit in the past, and the effect of this deformation grew with time. This is sometimes these authors call this the butterfly effect. That you had very tiny perturbation in this chaotic system, which we think that the Hamiltonian that of the field theories in the regime we are interested in is a chaotic Hamiltonian, which will amplify the effects of a perturbation. So making a little tiny perturbation in the past changed the state in an important way in the future, and so that's what we expect from the field theory side. And in the gravity side, the manifestation of that big change is the fact that the geometry got this big change. Okay, so that's.
So what are the dashed lines in this circle?
These dashed lines are null lines, right? And they are the horizons of the exterior black holes. So from the exterior point of view, we just have essentially an ordinary black hole, and we sent in a very tiny perturbation. Nothing much changed from the outside. Yes.
Usually, little changes that make big changes to Penrose diagrams have dramatic effects. Like, for instance, you throw a single electron.
Yeah. Yes.
Penrose diagram changes completely.
Yes.
And one expects the inner horizon.
Yes. Yes.
Aren't similar effects expected here when the Penrose diagram is dramatic?
Well, I mean, I don't know if you call this a dramatic change. So, for example, there is a qualitative change that these two horizons here were touching, and here they are at finite distance. I don't know. Do you call this a dramatic change? I don't know. This is the actual change that comes from looking at this particular process.
Clearly, there is no dramatic change to the physics, but there is dramatic change to the Penrose diagram. That's why I gave the example of the single electron.
Yes, yes. No, you're absolutely right. I mean, here these authors worked out the actual change of the Penrose diagram, and this is the final answer. So this is a dramatic change, and it's more and more. So if these two times are very close to each other or of order beta, there is no big change. And as the times get large, then there is a dramatic change. It's a bigger change. Yes.
The pentagonal region in between, which has just the path similarity, does it have a physical?
Say the question again. I didn't understand.
Sorry, the pentagonal region in between, which just has the path similarity.
Yes.
So does it have any physical significance?
You're asking what's the physical significance of the path singularity?
Yeah, and basically that region which has two future horizons, two past horizons. That forms the pentagon. What is it?
Pentagon made by the two broken line, by the wavy line.
Oh, this whole region. Yeah. So this whole region is inside the wormhole. I mean, it's a region which we would call inside the wormhole, right? Well, this is what you get in the geometry. So if you have that state, the idea is that that state would somehow be associated to this geometry, right? I mean, you can ask more detailed questions, like if I have an operator here, how do I realize it in the field theory and so on? And these are not questions we know the answer to. So, that's why I'm saying this is a phenomenology where we.
Here the wormhole hits the singularity.
Well, in all cases, the interior of the wormhole becomes singular. So in this case, it becomes singular. Here also, it becomes singular when you travel to the past and the future. In all cases, you cannot send signals through the wormhole and so on. Right? Now, another amusing feature of this example is the following. So we said that this this is an out-of-time order correlator. And if we were trying to evaluate this in a path integral description, we would do something like the following. So we would evolve up to T1, and then we are going backwards in time to T2, where we insert the other operator, and then we continue evolving to the future. So we have this kind of folds. So we could always say, well, we put this operator later, but this operator, because the time is earlier, includes some unitary transformation that sends it backwards in time. So we have, at least in some way, just thinking about the calculation, in a path integral description, we would do it with this fold. So conceptually, we have that fold. And an amusing feature of these geometries is that that fold is in some ways present in this geometry. So we have, if you look at this, if you look at the maximal volume slice between the two sides, these are the type of slices you could get for calculating these things like entanglement entropy and so on. It kind of goes in here and it hangs near the futures near this horizon for a while. And it has, so this piece going up is similar to this piece going up here. And the actual length of this region, the actual physical length, is actually the difference between these two times. As we make it larger, the physical length of this piece becomes larger. And this was, again, discussed in great detail in these papers. So this is some phenomenology. You can add more operators, many more operators. You could get more folds, and here you can get a longer wormhole with many things going in, and so many of these lines. You can imagine making the energies of these shocks very small and putting lots of them in such a way that you create a situation where you have a bunch of a gas of left and right moving particles here in the middle, and in this way you can make this as long as you want. So you can always do that. So here you can, I mean, a wormhole has this sphere that was shrinking, right? And we can keep the sphere fixed here by putting this gas of particles, right? In that way we can solve the constraints with an arbitrary long wormhole, and then they will evolve to the future. So we can make them arbitrarily long. And okay, so what are the lessons from this? Well, there are some well-defined constructions of numerous wormholes. The wormhole gets longer the more we complicate it, the more we perturb the state and we disturb the state, the wormhole gets longer. Note that these wormholes don't have to have a moment of time reflection symmetry. So here we emphasize the time reflection symmetry in order to construct and to argue that we had this wormhole. But that is not a generic feature of these wormholes. This wormhole doesn't have it, and neither has the one we discussed later and so on. So they don't have to have that moment of time reflection symmetry. And in these ones that contain many, many shocks, with these operators, many operators which are out of time order, we get that the length of this surface is proportional to the length, essentially, of these folds. So all of this is phenomenology, so it's just analyzing various solutions. Now, one question you can ask is whether these constructions give the typical state. So is it generic enough to give the typical state? And we don't know. So by typical state, so let me be more precise what we mean by a typical state. So let's consider a situation where we have two field theories, similar to the two field theories we had in this description. And we have, in each field theory, we have a state that looks like a black hole from the outside. So it's described by a density matrix of similar to the one with the same entropy as the one of the black hole, or identical density matrix to the one of the black hole. But the state need not be this one. So here, for example, we can act with a unitary transformation on the left, and that will not affect the density matrix on the left or on the right. And so we can have more generic states. Psi, so psi will be a generic maximally entangled state. And here, by maximally entangled, what we really mean is a state which is such that if we trace out, let's say, over the right side, for the left side, we have the usual black hole density matrix. Okay. So that's a typical state, and you can ask the question of what is the wormhole geometry, if there is one, for the typical state. So, and we don't know what the answer is for this case. So we don't know whether there is also geometry for that case. Okay. At least there is no clear argument that there is a geometry. Okay. Now, if this state is typical, then you can estimate the size of the correlation functions between two operators, one on the right and one on the left. And this type of correlation functions are a measure of the size of the length of the wormhole, if there is one. So if there is one, we expect that longer wormholes will have smaller values for these correlators. So what is the size of these correlators?
Sorry. Can I ask about the...
Yes.
If you're just computing correlator of just operating circuit on the left,
Yes.
For these bars separated
Yes.
in operating time, how would you do that computation since you seem to be losing the boundary source for T1, for the operating circuit at T1, from the bulk point of view?
No, okay. It's not that you are losing the boundary. I mean, you can actually insert the operators here, and then you take this. This is the background geometry. This is the state in which you are going to do the computation. And then on this state, now you insert the operators. And when you do that, then you have, let's say, the W. So for example, in this case, we have the W at T1, W at T2, right? So we can insert some operators on the left, right? And you would compute in this state. So you would do this computation, term of field double, and then W of T2, W of T1. So this is the computation we are doing, right? When we look at this geometry and we try to compute small perturbations on this geometry.
That's the thing divided by the background.
Yeah, that's the expectation value, and then we divide by the same thing without this. That's the expectation value. Yeah. What I'm emphasizing is that we are thinking of this as a new state, right? So we have this new state, and in this state we would do the whatever subsequent computations we are doing. Okay, so here one can estimate the value of these correlators. These were estimated by Marov and Polchinski, and they argued that they were of order, typically of order e to the minus s, where s is the entropy of the black hole. And so that's saying that the typical, if there is a wormhole, then it should be very long. Okay, so certainly we will not have for a typical state, we will not have one of these short wormholes with very small distance between the two sides. Okay. So the picture seems to be that wormholes in complicated states are long. Wormholes in very special states, like the thermophile double, can be very short. And so thermophile double seems to be as short as it could be. Okay, so that's the phenomenology of wormholes. Now the idea that ER is equal to EPR is that in some sense there is a wormhole for any case, and the wormhole might be geometric, might not be geometric, or but if there is a theory of quantum gravity in the bulk, so Joe was saying that we would like to have some kind of theory of quantum gravity in the bulk, independently defined, so not defined by the boundary theory, but defined independently. And that theory should have the feature that when you have entangled states, you should have this type of wormholes connecting them. And it would be funny to have those wormholes connecting them between only special states and not for generic states. So let's say if there is a gauge gravity dual for a system, so okay, let me just make a small philosophical comment. So if there is indeed some independently defined theory of quantum gravity in the bulk, then we expect that as we consider various boundary theories, there should be the corresponding bulk theory. So we could start with one of the examples of gauge gravity duality and then deform it in any way we want and go to various field theories, and they all should have some kind of gravity dual. Of course, the gravity dual might be strongly coupled, so it will not be described by Einstein theory, but by some putative general theory, exact theory that would be the theory that we would like to find eventually. So if that were true, then any system should have a gravity dual, including, let's say, a spin-a-half system. So is this?
Is what you're saying is if I take, for example, ADS.
Yes.
Who's dual we want?
Yeah.
A strongly coupled dual.
Yeah.
And now I just I create two gravitons which are entangled.
Yeah.
In a bond.
Yes.
The geometry changes in such a way that there's a wormhole between those two gravitons.
Well, yeah. So the standard description of that is if you have two separate, if you have two gravitons, you just have the two gravitons. There is no visible wormhole. They're entangled, and the standard description is that there is no visible wormhole. So let's just imagine. So let me make one. So imagine you create here a bunch of spins and so on, and that these spins are discretizing n equal to 4 super Young mills, right? So you create here a system of spins which are in some state which is the same state that you get for, let's say, n equal to 4 super Young mills in some discretization of it. And you do the same here, right? So then you expect that there will be a gravity dual to these guys, which comes out. So in this idea space, as you approach these spins, well, you have the spins, but then when you go to what we normally call the interior, so these are the spins. As you approach the spins, there will be what we normally call some near horizon geometry, right? We cannot trust the geometric description near the spins, but there is some sense in which there is some geometry here. This geometry is characterizing some kind of collective properties of these spins, right? It's the same way we think about the geometries in ideas. And if these two systems are entangled, then we expect that for these spins, they will be connected by the wormhole, for example, of the thermofield double. If these two are in the thermofield double, then the same argument we saw before will connect them, right? And now you can say, well, if this holds for many, many spins, should it hold for one spin, right? For just only one spin. So for one spin, we might have some very quantum geometry, which certainly will not be described by Einstein theory. It's one would never say that because that would be wrong. But the idea is, if there was geometry for any finite number of spins, well, why couldn't there be a geometry for one spin? And if there isn't a geometry for one spin, then why would there be a geometry for a finite number of spins? So you see, if you assume that this is not true, okay, then you are also saying that in some sense, even for a finite number of spins, for finite ADS and so on, it's also not true. So there is something.
Why couldn't it happen only in
Right. So then, you could take the point of view that gravity only makes sense thermodynamically, right? So that means that gravity will not be an exact theory. It's not an exact description valid for finite n that gives you a completely fine-grained description, right? So the hope that Joe was expressing of finding a dual description for gravity, some gravity, sorry, not a dual description, finding a bulk description for gravity which is exact and so on, would not be necessarily realized, because from the point of view we're exposing now is the idea that gravity would be some kind of thermodynamic approximation only. And this might be the correct answer, so let's...
The quantum gravity.
Quantum gravity, yes. Of course, classical gravity, there is no contradiction in thinking that classical gravity might be some kind of approximation. So the question is whether the quantum version makes sense exactly or only in perturbation theory. Okay. So one possibility is that gravity only makes sense in perturbation theory. Some intrinsic approximation is like hydrodynamics. We could say gravity is the hydrodynamics of entanglement. Tells us how things are entangled, how is some version of the RG group, and so on. And it only makes sense in some kind of large n limit. I think both of the possibilities are interesting, and we don't know which is the correct one.
So this
and
would be EPR entangled, these two spins.
Yeah, these two spins are EPR entangled, and yeah.
Isn't there a quantitative relation between entanglement and the wormholes? I understand we want to relate entanglement and wormholes.
Yes.
Now, entanglement we know how to measure. We know how to measure the entropy of entanglement.
Yes.
Wormholes, I can...
Well, I actually dispute this. So just a second. Entanglement is a funny notion, and there is no operator that tells you whether two things are entangled or not. Okay, because so you can measure a particular pattern of entanglement, but not the question of whether you are entangled. So if you have, so imagine that we want to find an entanglement operator, right? Whose eigenvalue will be 1 when the system is entangled, and let's say 0 when it's not entangled, right? Let's say for two spins. So we have two spins, the EPR pair, usual pair, and we want to define an operator that has these properties, right? So such operator does not exist, because you can realize the EPR pair as a sum of two states, right, which are not entangled, right? Each of the two states are not entangled, and therefore we would get 0, acting here, and we take the sum, and we are supposed to get non-zero, right? So this shows that this is not a really good notion. It's not a really proper notion. And now you can ask another question, which is whether these two states are in a Bell pair, in the particular Bell pair where this is plus and minus. So let's say it spins 0 in this particular state. So let's call this psi, right? So then there would be a state that tests this, which is just simply this operator, right? So this one tells you whether you are there or not, where you are in this state or not. But you cannot say just entangled. And so then you can say, but wait, you can still measure the entropy of entanglement. So therefore, if you do that, why couldn't you just compute the entropy, and then you would know? But you should realize that entropy is also not a linear operator, because entropy is equal to trace of rho log rho, right? While any linear operator, expectation value of any linear operator is trace of rho times some operator. Okay, so it should be linear in the density matrix. This is non-linear in the density matrix. Okay, so this entanglement entropy and so on is not a measurable notion. It's not measurable in the standard, according to the standard rules. Of course, it's proven to be somewhat theoretically useful and so on, and it has all nice properties, but we shouldn't forget that it's not measurable in the standard way.
So this even makes my question
more relevant. Okay, yeah, go ahead.
I'm not sure if I
Yeah.
could discuss this further, but presumably you can imagine trying to measure somehow the wormhole next by its size,
The wormholeness is a property of the gravity solution. I don't know how to define wormholeness from the field theory side. So the field theory side, there is two things. I mean, a necessary condition, of course, is that the two systems are entangled. But
But you claim a relation between two notions.
yeah. So the claim is that whenever they are entangled, there will be some kind of wormhole. That's the
What is
that's
some
no.
kind of wormhole? Some kind of wormhole.
Well, it's I don't know what it means because we don't know what the general theory of quantum gravity is.
But it's supposed to be, so it's supposed to be regarded as something that looks like a wormhole in the classical geometry.
Yeah.
That is a good approximation to the quantum.
Yeah. So the statement is that this is some kind of wormhole, and this kind of wormhole becomes a very concrete wormhole in some special circumstances. Yes, for some special states. It's in the same sense that you could say that any quantum system has a gravity dual, but in general we don't know what the gravity dual is. And for some very special systems we know what the gravity dual is. And we don't expect generic quantum systems to have a simple gravity dual, even generic large-n systems.
Or even a notion of what a wormhole.
Well, the idea is that the notion of the wormhole would be the same as the notion of the gravity dual. So, so when we say we have a gravity dual, right? Okay, there's the gravity dual of a spin-and-a-half system or two spin-and-a-half system. What is this? So we don't have an independent definition. Only for some very special theories we have an independent definition.
I guess what bothers me is if I think of the gravity dual being, I mean, it's just two entangled gravitons in the background of the S-phase.
Yes.
I don't see where the wormhole.
Yeah,
I'm now thinking about the entanglement in the bulk.
Yes.
Create two gravitons.
Yeah.
And they're entangled.
Yes.
Is there a wormhole in that geometry? I think of that as ADS.
Yeah. You think of ADS with the two gravitons. In that description, there is no wormhole.
Where's the wormhole?
Well, you have to go inside the graviton somehow, inside the degrees of freedom of the graviton. You have to find the gravity dual of the graviton, of a single graviton.
Well, we sort of know what that is.
Well, we have a description of the graviton as perturbations on the original background, and in that description, indeed, you are absolutely right. There is no wormhole.
So that description somehow already washes out the entanglement.
Well, I would say that this is a description of these gravitons from the outside, and then there is the wormhole exists inside, right? So the wormhole is this little line, the entanglement between the two gravitons is some little line that you have to go somehow inside the degrees of freedom. So you have to go to the gravity dual of this spin. Let's say you entangle the spins of the gravitons. You have to go inside this geometry, let's say, of the spins of the graviton, and there you would have the wormhole. This is vague. Let me.
Can you measure the wormhole by computing the left and right correlators, just by saying that it agrees with some perturbative bulk computation?
I mean, certainly in cases where you have these examples, for example, you can compare some gauge theory computation to some bulk computation, and you would check whether it's correct or not. Yeah.
The relation between entanglement and correlation. Can you say something about that? My impression is that entanglement, in some sense, measures all possible correlators rather than specific ones. Is that a fair?
Well, I mean, the difference between entanglement makes possible the quantum correlations, right? So correlations that violate Bell's inequalities. So it's more than classical correlations. So it's the particular kind of correlations we have in the quantum theory, where non-commuting operators can be correlated at the same time, right? So we have two spins. We measure sigma c and sigma c. They are correlated. We measure sigma x, and they are correlated. And this fact is something peculiar of quantum mechanics that is not possible in the classical theory, or at least.
The statement about the two-point function measuring the length of the wormhole, is there something you can actually calculate from the field theory side? That you can actually get the actual correct length?
So you in principle you can you can calculate some operator. If you have some operator whose correlator is given by some geodesic, you can compare the two pictures and get the length in principle.
But in practice?
Well, in practice, I mean, I'm not sure what kind of distinction you want to draw. I mean, in practice, we cannot calculate correlators in strongly coupled field theories. But if there is a computation that if you had a big enough computer, you could do in the strongly coupled field theory and compare to some computation you can do in this wormhole. And the idea is that these two computations should match.
So that requires at least a compute that 6-point function to for numbers.
Yeah. So, I mean, this is, you should view this as a requirement of what we would like, what we think we want from a gravity theory. It's not a theory. I mean, it's not. So the way that gauge gravity duality should work is that when you have entanglement, you also have geometric connection. So we don't have separate geometries for the separate systems. So we have two separate systems. We don't have separate geometries for them. We can have connected geometries when we have entanglement. And this is something that is important to keep in mind. Okay, so I'll now would like to and I mean, hopefully later I'll probably discuss some bigger ideas where you can see how something like this could be realized. But now I like to give an analysis of the AMPS paradox, so the AMPS 1 paper. So their first paper, in the context of this thermofield double and so on, and to see what, well, we will see that there are some new features. So basically what they noticed in their paper is that if you have a black hole that is very old, so it's maximally entangled with radiation. So here we have some other second quantum system, let's call it radiation. And these two are in a state which is maximally entangled. So all the microstates of the black hole are maximally entangled with states of the radiation. Then they said, well, we focus on some mode B here, some particular near horizon mode. This mode is supposed to be entangled with some mode in the interior. Let me draw the Penrose diagram relevant here. So we have some mode B that lives here. There is some mode A living in the interior. And these two are supposed to be essentially entangled with each other. But at the same time, since the black hole is maximally entangled and this mode B is eventually going to carry some non-trivial information, this mode B is also maximally entangled with the radiation. And so you can take this radiation and act with a unitary transformation, so with a quantum computer, some unitary transformation, and you can select some mode, some particular qubit RB, which is maximally entangled with this mode B here. Okay. So here we've done this distillation of the entangled. We've found a particular qubit that is entangled with B. Okay. And now we apparently have a contradiction because this mode B is entangled with two things, and the strong subadditivity inequality does not allow such a thing. Okay, so that was their discussion. So let's now do the following. So we'll modify this a little bit. So we'll say that we will not only distillate these qubits, but we'll collapse this into a new black hole. So we'll collapse this into a new black hole, B, in such a way, I mean, here it's assumed that you know the initial state. You knew the initial quantum state. And so that's why you could find this, that's why you could run this quantum computer and find this. And if you know that initial state, you can also collapse this system into a second, this system of radiation, into a second black hole, which is in the thermofield double with respect to the first black hole. Okay? So here we are assuming that there are no restrictions on the kind of quantum computations we can do. It was also argued by Hayden and Preskill, Hayden and Harlow, that you couldn't do this in finite time. But we're not going to ignore that that distinction. Let's imagine we somehow could do it. Then we do this, and this amounts to a perfect distillation of not only B but all possible qubits. Because why is that? Because now we can draw a diagram which looks like this. So we had this old black hole. We had this mode B we've been talking about. And the mode RB, the one that is entangled with this, is, well, this mode, corresponding mode on the other side. So in general, modes here in flat space are this mode is entangled with this one. And we can see in the field theory very clearly how these ones are entangled. And these differ by some boost. So here we have the mode RB is the mode that initially was here in the radiation. Now we collapse it into a black hole, and that particular qubit is one corresponding to a field theory mode outside the horizon. Okay, so that's the mode RB. Okay, and it is indeed entangled with B, right? So far no issue. But now let's see what mode A is. So mode A lives here, and mode A is actually in the future of RB. And so there is no problem in having these two, these two maximally entangled and also these two maximally entangled. Because the problem with violating the strong additivity condition and so on is when you have three separate qubits that are not causally related. But here in this bulk theory, A is causally related to RB, and therefore there is no problem. Okay. So what this shows is that that if entanglement can create a geometry, right, some geometry in the interior, then we have to be careful about arguments which involve spatial. So here the basic logic here in the argument is we have this radiation here outside, and well, we have some space-like section which where all these qubits look like they are completely independent. But if there is a geometric, somehow these qubits generate a geometric connection which connects somehow to this interior, then that argument is not. That is not true anymore, and the strong pseudo-additivity condition doesn't have to hold. And furthermore, what Amps also said is that if we take this mode RB and we carry it and we fall into the black hole, we can actually measure these three particles, but now they're measured by a local observer who actually can measure the three things, and we'd better get something reasonable, right? So, what would happen in this situation? So in this situation, if let's consider the ADS version of this, and so we view this as living in some field theory. And so we can imagine that these are field theories living in a lab, let's say, and there is an experimentalist in the lab that can measure this qubit, can extract it, and take it to the other side and send it to an observer that will then fall in, right? So if we did that, then we would disturb this, we would change this qubit, and now we will have a signal that is coming here, and bit A will not be what it was before, and indeed, as Amps suggested, when we try to do this, we will not find that the three qubits are entangled as we naively expected, but we'll find that the qubit A is not in the state it was. Okay. So that says that if we take this qubit and carry it, we indeed find the problem as they suggested. But the question is where we find the problem without distilling, without doing anything. So what this example suggests is that doing something or not doing something changes your answer. Okay.
In the thought experiment of distilling changes.
Yeah, the idea that you take, so distilling by itself doesn't do much. I mean, at least in this case, if you form this particular state, it's perfectly smooth. But if you take out this qubit and so on, you will do something. And so what this is arguing is the following. So if you take this radiation, you collapse it into a black hole and so on, there are all these indirect arguments which says that if you form the thermofield double, there is nothing that happens. So at least this shows that if all this is true, then doing that, so here this process that formed the black hole and so on affected what you would see here. I mean, or at least is relevant. So the fact that there could be a geometric connection between these two sites is relevant for the analysis of this setup, right? So that's the main point. So the main point is that it is relevant. Now, notice, by the way, that people sometimes say that this notion of ER equal to EPR is the same as saying that RB is equal to A, okay? And that this then is wrong for some other reasons. This is not what this is saying, because if, suppose an observer comes in here and measures A or changes the state of A, right? Projects A and so on. That's not expected to be a measurement of RB. So the observer here outside, so this qubit RB, some degree of freedom of this black hole, and we don't expect that someone falling in here on this side can affect this qubit in any possible way. Okay? So this is some interior region whose existence we need to figure out what the rules are. So what I'm saying is that the rule is not that RB is equal to A. The rule is more subtle. I'm not giving you what the rule is. I'm just doing phenomenology of saying what we expect the rule to be. Now, what this shows is that in this particular setup, by modifying this, we can send the signal behind here. And so what AMPS so the second paper that they wrote, they said, well, if you do a simple change, so if you assume some relation of this type where the mode A depends on the radiation, for example, that there is some communication, then any simple change of radiation, like changing one of these qubits of radiation, will generically send a signal here. Because if you think that there is a simple unitary relation between A and whatever modes you have here, and if that unitary relation is very complicated, then any simple measurement here will not commute with the operator here, A, and therefore by doing that simple measurement you would get that change. I'm not sure if Joe discussed this in his lectures. Not in detail. Anyway, you will do that today? No. Okay. Well, now what did we learn from the phenomenology of wormholes we studied? Right. So one thing we learned was that the wormholes were getting longer and longer as we complicated the state, and so if we now do what is like a simple change of a state here on this side, we generically will make a perturbation that goes here, but it doesn't go behind the horizon here. So in order to get something behind the horizon, we first need to uncomplicate the state, so distill it, shrink it, and then you can send the signal. So now this is not a proof because we don't know what the generic wormhole is. This might be very special ones, and but at least it seems to offer the possibility that perhaps easy measurements do not perturb the region behind the horizon. For that to be true, then it has to be that the map between the states here and the states behind the horizon is somehow not solid. It's not a unitary transformation. It's definitely not somehow of this type of form people are imagining. And I think it's our job to figure out what the rules are. So, but from the phenomenology of wormholes, it looks like we could have a rule of this kind that has this feature. Okay, so I have 25 minutes. Yeah. Okay, so now I like to. So all of these were some remarks on these features, and now I like to discuss some.
So the conclusion, your conclusion is if you figure out these rules, you would be saying that nothing happens to an observer falling through the firewall. Is that firewall?
Yeah.
And you don't have to modify quantum mechanics.
Well, we didn't give a rule, so we didn't give a rule. So we'll just do this. There's some phenomenology of wormholes. We say that we don't know what the rules are, but the rule seems to be that the interior is created in some funny way from entanglement, and that according to this, it might be that, that there is no firewall, but there is no proof. So I think a full resolution of the paradox involves giving a concrete, more concrete construction of the interior Hilbert space, where you really see that you don't run into the problems that they suggested. But so what they said, what they showed is that if you attempt to construct the interior by thinking of operators in the interior as operators that act on some Hilbert space, either the Hilbert space of microstates of the black hole or the radiation, you run into a problem. And this is correct, and no one, I think, is disputing this. So so that's so we need a different construction. And so far, I think no one has given a construction which is free of problems. And so ER equal to EPR is a feature that the correct construction should have, that, for example, the construction they assumed did not have. So that's all.
Can I ask still about the earlier description of the wormhole in
Yes.
terms of the two W's right now, the multi double?
Yeah.
You say even though the shock waves cause large back reaction, somehow it does not affect the computation of the correlators all left and all right very much? You just use the...
Well, it affects them a little bit, and it's been discussed in the papers. But yeah, so the idea is that the particle crosses in a region where the shock wave is not important. It's not very large.
And that seems to be an important feature for the strongly coupled field theory that's going to be destroyed before, say, weakly coupled field theory. Because you want to say the shock wave are localized in space-time.
Well, the shock wave becomes, so there's this boost, and if you cross early enough, the shock wave is not very important. But if you go further, closer to this bifurcation point, it becomes larger.
It seems to be a remarkable statement that for generic W, you create kind of a smooth jump for wormhole, and that's a feature that I think would be lost if you do this for weak double gauge theory on boundary.
Oh yeah, no, that I think what is necessary is what is necessary. So let me just say what we would like to be true. Okay, so in order to have a smooth horizon. So if we want a smooth horizon, so we have our black hole, right, and we have the radiation or any second system, and what we want is some kind of wormhole that is smooth. So this is the horizon. So it's smooth just behind the horizon, but then it could be very non-smooth. So when it connects with the radiation, it's certainly not very smooth, because we have all the various qubits. They are very well recognized. We can't see any recognizable wormhole here on the right-hand side, right? So it's very non-geometric here. It's like the gravity dual of a bunch of spins. It's not something very, very easy to recognize. But then the idea is that it should be geometric just behind the horizon. So the minimal thing we would like to be true is, so if we have the black hole, let's say this is the exterior, and so where should these wormholes connect? Well, they should somehow connect here. So here we can have non-geometric things, but we should have something geometric in this region. That's what we would like to be true. And yeah, so this is yeah.
How much of this, just to get some perspective, how much of these ideas carry over to the case if I would consider a physical collapse of matter into a black hole?
So everything that I was discussing here has to do with black holes which are maximally entangled with a second system. And the reason for discussing this is that it is in that case that you seem to run into important paradoxes. So for a black hole that collapses, there is no, at least if you don't wait for long enough, there is no obvious contradiction. But the contradiction becomes more clear when you have a very old black hole that has evolved for a long time and then is maximally entangled. Because then you have this feature that you want entanglement to be shared with two different systems.
So this idea of ER equals ETR or any similar extension would not, there's no obvious way to extend that into black holes that are physically formed.
Yeah, so if the black hole is physically formed, so let's say you have. So the idea is that so you have again the exterior, right, and the quantum degrees of freedom somehow are in the exterior, and the interior is some kind of bridge that connects one region of the horizon with another region of the horizon, similar to what you have in ADS. I'll probably discuss this a little more now, but already in ADS you have some connection in the interior of different boundary points, right? If you look at the spatial slice, you have some connection. You can view that as also some kind of bridge that connects them.
But if you create a black hole from quanta which are maximally entangled
to something else, then yeah.
Then you have a wormhole.
Yeah, then you are in this situation. Yeah, then you expect to have some kind of wormhole. And so suddenly that thermal field double example shows that the smoothness of the horizon depends on the actual pattern of entanglement. You cannot decide it you cannot decide it just by looking at the density matrix of one black hole. What happens when you fall into the black hole depends on the second black hole. So let me be more. Let me emphasize this point a little more. So here you have some black hole here, and from the point of view of the exterior, the black hole is completely determined by its density matrix. Okay. Now, when you fall in, what you see here depends on what this guy sends you. Okay. So here you can perturb the system here without modifying the density matrix at all. Okay. But what you see when you cross in depends on what this guy sends you. Okay. So this means that when you go to the interior, you need something more. You need a little more information than the one contained in this density matrix. So, okay. Now there is one point of view which says, well, this is a very special state. I'm going to ignore it for the whole discussion, never think about this. And so that's a possible point of view. I'm going to ignore anything that comes from wormholes. We never really have these connected spaces. We're going to ignore it. But I think, yeah, so that's a possibility. But I think this possibility is ignoring some of the simplest solutions we have in GR. This is the simplest non-trivial solution of GR, spherically symmetric. And we might be just throwing away one of the best lessons we have in learning how quantum gravity works. So I think we probably will make more progress by taking it seriously than by saying that by ignoring this. Yeah.
If I understand correctly, then this means very bizarre things for the interior of the black hole.
Yes.
Like, for instance, I always thought we could have lived inside the Unity black hole, but
Yes.
that means that what is happening to us now is completely out of control.
Well, in some sense, at any point we can have some signal coming to us and destroying us, and a domain wall that is, the universe is decaying to something, and this can definitely happen. Okay. I don't know. Yeah.
If I have an invariant system,
Yeah.
it's a superposition of states, and I measure it, and it collapses, and the wormhole just vanishes.
Yeah. Yeah. So after the projection, yeah. After the projection, the wormhole is not there anymore. Yes. Okay. So I would now like to discuss. Well, this talk this part of the talk will be a little more. Well, the relationship to gravity will be more qualitative. What I'm going to discuss here is fairly solid, but it's some developments in condensed matter which are called tensile networks. And this has to do with thinking about the renormalization group for the wave function, what it means, what the normalization group really means for the wave function, and trying to get concrete pictures for the wave function of spins. So imagine you have a system of spins. So we have the spin 1, 2. So here, forget about gravity. So we'll get back to gravity later. So for the moment, I'm going to establish some notation and give you a few facts. So imagine you have a spin system, and you're trying to find the wave function for this spin system. So we have the spin S1, which could be plus or minus, and so on, SL, which again could be plus or minus. So we have all these spins, and in principle, determination of the wave function involves giving these 2 to the L complex numbers, one for each choice of sign here, that describe the wave function. So that's the full Hilbert space of the system. Now, in people in condensed matter sort of notice that if you are looking at special states, like the ground state of this spin chain, and small excitations around the ground state, that whole discussion takes place in a smaller subset of this Hilbert space. So it's just the ground state and those excitations, which is a far smaller set of states. So somehow you have the Hilbert space is very big, and the whole dynamics is happening in a smaller part. So it would be nicer to have a description of just that smaller part. Now, let's consider a spin chain, and let's consider Hamiltonian such that the ground state is gapped. So gap means that correlations decay with distance. Okay, so when you have look at correlations, they decay with distance, and we'll try to describe such a state. And it's found that it's convenient a convenient way to describe such states is to make an ansatz for this wave function, where you say that, let's imagine the spin chain is periodic. So we'll make an ansatz where we write this wave function in terms of tensors, of a matrix. So this is a tensor which has 3 indices, so Ts. So one index is S. So we have, and you can think that for each value of S, we have a D by D matrix. Okay, so these indices go from 1 to D. Okay, so we have a D by D matrix. And then we take the trace over these indices, and this is some ansatz for the wave function. Not all wave functions can be written this way. In fact, the number of wave functions that can be written this way is so the dimension of space of wave functions that can be written this way is equal to, well, we have D squared complex numbers for the tensor times 2 for the 2 indices for each one. And so that's the dimension of the space. And for finite D, this and for large L, this is much smaller than 2 to the L, right? So the space of wave functions you can write this way is much smaller. I mean, you can even make these tensors different. So one tensor then for the, and even if you make them different, all you get is an extra factor of L here, which for large L is still continues to be much smaller. Okay, so this is describing a set of states which is much smaller than the original set of states. Now, one feature of, just in order to understand what kind of states this describes, this could possibly describe, let's try to, well, let me first draw a picture for this. So a picture people draw for this is the following. So we have, we represent each tensor by a vertex. And the indices of the tensor are, for example, for this tensor is S1, and then we have the L and J index here, right? And so the J index of the first tensor is contracted with the J index of the second tensor. That's a line that goes between one and the other. So this represents a contracted index. And here there is the S2 index and so on. And so this is a graphical representation of these tensors. And this looks like a network, and that's why they're called tensor networks. This particular one is called matrix product state. There are lots of names people choose for each particular one, but for our purposes, all that will be important is that we can draw these graphs with tensors at the intersections. Now, if we calculate the entanglement entropy of a system like this, where we separate, let's now consider, for example, an infinite system. well, or not infinite, but very large. And we consider a finite part of the system. From this picture, we can imagine calculating the entanglement entropy. And the only thing that is entangling this to the rest of the system, the rest of the wave function, is the sum over these indices. Okay, so it is then intuitively clear that the entanglement entropy that will come by dividing an infinite system like this into two parts will just be bounded above by the number of indices we have here, right? So the entanglement entropy of dividing the system into two pieces, it will be less or equal than the log of the number of indices we had, right? So then it's clear that the only kind of systems that can possibly have such a representation are systems where the entanglement entropy is finite, right? So when you divide the system into two pieces, we have a finite entanglement entropy, and then if we take D to be large enough so that D is bigger than the entanglement entropy, then this will give a reasonable characterization of the state. Okay? And people who do numerical simulations in condensed matter and so on, they find that this is typically good, and you take D a little bigger than the entanglement entropy, and it works nicely. So an example of a case where it doesn't work is if you take a conformal invariance theory. So imagine that this is a spin system whose ground state is ungapped. So it's, let's say, the theory becomes conformal in the infrared. So if the theory becomes conformal in the infrared, then this is not a good description of the system. And because in that case, the entanglement entropy in the infrared, recall it will go like, right, epsilon here is of order 1, is the lattice spacing, and L is the, it's infinite for an infinite system, so it doesn't work. So in that case, you need something a little more sophisticated. So you start with this, so you have all these indices of the wave function, and now you will contract them in pairs like this. And you will introduce now some 5 index tensors. So I'm giving a slightly simplified version of this. So you construct your tensor network in the following way. So you take here, this will be a 5 index tensor. So here 2 of the indices are S1, S2, and then all these 3 are internal indices. Now once we get to the next level, all 5 of the indices are all internal. Okay. Yeah, I should have said that you can think of this as some other state in some state in a bigger system where the indices are also physical, right? And again, that the state is entangled and so on. But these indices appear here are completely auxiliary. They are not present in the original system. They are completely auxiliary indices. And the same is true in this construction. And so once you get deep inside this network, all you have are these 5 index tensors. And if you look at this picture long enough, you can realize, and Brian Swingle realized, that it looks very much like those Escher pictures of ADS space. Okay. And well, by the way, people find that using this type of tensor networks, you get a good description for the ground state of these systems. Now, I'm going to make a side comment, which is when you go and actually look at the papers, they really like to construct these tensor networks in such a way that they can be viewed as a unitary transformation from a system of decoupled spins to a system to the final ground state. And there are a couple of reasons why they like to think about it this way. One is because it would give you a construction of the state. And the second is because when you calculate some correlation function, all the spins that are, you can forget about everything that is somehow causally disconnected. So when you calculate psi star, there will be a bunch of things that cancel out, and that's also another convenient thing. And so if you think about it like that, like as a unitary set of unitary transformations, So here, of course, this looks funny because we have here more things coming out, but you can add another line here where you put one particular value of the index, right? And in this way, you now have that's how they get the unitary transformation, essentially, right? So you get the unitary transformation. You can think of this as some kind of Hamiltonian that acts on a system where you start with some things in the ground state, and then they generate some entanglement. And then this looks very much like de Sitter evolution, right? So in de Sitter, we also have the degrees of freedom that come from the ultraviolet, which are that they always come in the ground state, and then the de Sitter evolution creates the entanglement and creates a state in the far future, which is of course very entangled and contains the usual fluctuations and so on. So this idea of thinking about the tensor network is also particularly, I mean, it really is almost directly the description of dynamics in the Sitter space. So this was a side comment. Side comment. So, and might be useful for thinking about the Sitter space. But
sorry, in that case, you think of it as unitary transformation. I mean, here
yes.
it's a variational wave function.
Yeah, here it's just a variational. In all cases, you can view it as a variational wave function.
So for each variational wave function, you have to
No. You can choose these matrices as whatever you want, and they sometimes choose it to be unitary for practical reasons. I don't see why you need to choose them unitary for their purposes. I'm only making the comment that in the de Sitter context, it's natural to have them unitary.
But if I then try to apply the ground state by
yes.
variational techniques,
yes.
I will find a unitary network?
No, from their point of view, they just choose to have a unitary network. They can do whatever you want. So I asked them, why you choose a unitary network? Just for convenience, not any fundamental reason.
But that's a restriction on the passive trial wave function, so it might not
yes.
be the ground state.
No, but well, in practice, it gives them the ground state, and the thing is that you have here freedom to choose whatever tensors you want. So you can the statement is you can choose them to be unitary, and it makes some physical sense to think that you can choose them to be unitary, because you should be able to construct a wave function out of decoupled spins. So you have a bunch of a product state of spins, so all spins in the ground state, and then you apply a unitary transformation to construct the actual final state. And their method, or these tensor network methods, give you a prescription for how to do it, and how to do it in a simple way, because you have a finite number of operations, relatively small number of operations you need to do to get to this wave function. So it's not this shows that the ground state wave function of this system is not arbitrarily complicated. It has a certain simplicity in it, and in the language of quantum computing, it can be done in, let's say, polynomial time. It's not a NP hard problem or whatever. It's to construct the wave function once you know the tensors.
So the tensor has one index for each line. Is that how we read this diagram?
Yeah.
So those contract indexes you have.
Yeah. So let me be more clear. So here this is a tensor. So let me take one in the bulk here. Let me ignore this line. So this is some tensor that has 5 indices. So this is I, J, K, L, M. All 5 indices are contracted with other tensors, right? These tensors here are slightly different because these indices are really the external ones and have values 1 and 2. These values run from 1 to D. These are completely internal. Okay. Yeah, so the idea here in practice, what people do is that by taking tensors which are big enough, they get a good approximation. And to get an exact approximation, you probably need to take the number of indices to infinity. But most of the...
No, I meant also horizontally, you can read the state at every horizontal line.
No, the state is only read here, right? All the states here in the middle are just some approximation or some I mean, these indices D are not physical. They are some auxiliary construction. And this is so this is related to the renormalization group because looking at the system at this stage or at that stage corresponds to doing some coarse graining, and well, that coarse grained wave function is defined in terms of this. So you can cut it here somehow, and now you have a coarse grained wave function which contains these indices D, which are completely auxiliary. They were somewhat related to the original indices, but they're completely auxiliary.
Well, if
Yes.
you want to calculate correlation function in this state,
Yes.
how do you calculate? What is the spin acting on this?
Yeah, sure, yeah. No, this is simple. So the idea is if you have some operator, so you so you calculate, for example, sigma x at 1 and sigma. Yeah, so let's say sigma x at 1. Let's say you want to calculate this expectation value, right? So that then you take this wave function where one of the spins is the first spin is 1, and the rest spins you sum over the rest of the spins, and the second spin is 2, right? 1 and 2, or plus, let's say, up. The usual description how sigma c acts. So this is the complex conjugate wave function, and then you sum the other one, just the usual. So here all the other spins are summed over, right?
Okay, so it's just particular tensor that you choose.
And then and well, here you substitute these tensors. So in graphical, this is simpler to show in graphical notation. So we have the wave function for psi and psi bar. So we contract all the S indices, and here we put the sigma x, okay? Right, so the operator we only put here, then we contract over all these indices. And so if you imagine you want to calculate different operators here, sigma x, sigma y, etc. So one thing you can do is you can do this contraction once and for all, and then here put the different operators. And then you will get something which, well, you have the indices here sigma, and then there is something that comes from contracting all of these things, right? And so you have here just purely this. No, I didn't. I didn't because the value of t depends on the system you have. So if you have, let's say, different spin chains, you have different Hamiltonians, you will have different matrices t. So the matrix t is chosen in such a way that this wave function minimizes the energy. Right? And while computing it is found that there are some algorithms for more or less efficiently computing t. But I'm not focusing so much on why this is useful. What the main point I'm trying to emphasize is that this representation focuses on the states that are relevant. And well, it's then useful in practice. And here in the case of anti-de Sitter, we also have this more complicated. Sorry, in the case of a scale invariant system, we have this more complicated discussion, which looks very similar to. So let's just say that we define geometry to be the network itself. Okay. Now let me just do something first. So imagine we had this this tensor network, and so in the ground state, and now we considered some set of excitations. Let's say we put some excitations here and some other excitations here along the chain, and in such a way that they are entangled with each other, right? In order to represent that set of excitations with additional entanglement, we would not be able to do it this way if we put a lot of entanglement, but we will need to have additional lines that go between these faraway points, right? So in this representation, the tensor network itself contains the lines. So it's if you define geometry to be just the network, it has all the features that we want in. I mean, entanglement corresponds to adding lines and so on. But of course, these networks are very far from geometry. I mean, we don't really have this notion of smooth geometry or anything, and of course they are completely general. So even for, let's say, free systems, you can have this. Even for one single free fermion in one dimension, you can have this. So there is no large n implicit here. So the idea is that when you take large n systems or you take more complicated systems, then these networks have much more structure that will eventually, I don't know how to do this, but will have much more structure which reproduces regions of ideas. So the idea is that each tensor here is like one pentagonal region in ADS space that is connected to the next pentagonal region. I guess I should draw that. What?
That could be hexagonal. You should have easier tiling with hexagons.
No. Yeah. Well, it is true. In that's why I was not able to do it. I need a hyperbolic blackboard. But so in hyperbolic space, you can tile it with regular pentagons, and then you find. So the idea is that each tensor would be related to the state of the fields in ADS within this pentagon. With the fields are entangled to the next pentagon, but that entanglement is purely coming from this internal index, right? So it's completely auxiliary, and of course they all describe in this single state and so on. So something that is nice about the tensor networks is that, well, it's a completely auxiliary construction, and also the entanglement you have between, let's say, two. Here in the bulk, you can say, well, because we are summing over this index, we have some entanglement between these two regions. But yeah, so it might be the true entanglement or not, depending on what you are doing. Okay, I guess I'll finish here and continue next time.
I think that we have a